For decades, scientists treated Mount Vesuvius and Mount Etna as separate problems. Two dangerous volcanoes, two independent monitoring systems, two distinct threat zones. The assumption was straightforward. Vesuvius looms over Naples in the northwest, Etna dominates the Sicilian skyline in the southeast, and the roughly 140 kilometers of Italian terrain between them was simply geography. Background: irrelevant. What researchers working with deep seismic tomography data have now confirmed has fundamentally changed that assumption, and the implications for millions of people living across southern Italy are something that every serious conversation about European geological risk now has to reckon with. A connected magmatic plumbing system. 140 kilometers long. Threading beneath two of the most historically destructive, most densely monitored, and most culturally significant volcanoes on the planet. This isn't a fringe hypothesis anymore. It isn't a speculative model generated from incomplete data. The confirmation has arrived, and what it means. For eruption forecasting, for regional hazard assessments, for the 3 million people in the Naples metropolitan area and the millions more living in Etna's shadow across eastern Sicily, is something scientists are still working through. So let's work through it together. What exactly was found? How does a 140-kilometer magma network function beneath solid rock? What does history suggest about volcanoes that share deep plumbing? And what are Italy's monitoring systems showing right now in the context of this newly confirmed picture? These are the questions this video is going to answer, carefully, accurately, and with the full weight of what the science is actually telling us. Because the science is telling us something worth paying very close attention to. To understand why this discovery rewrites the threat assessment for southern Italy, you have to first appreciate what each of these volcanoes represents on its own, because independently, they are already two of the most watched, most feared, and most consequential geological systems in the entire world. Before we can grasp what a connection between them means, we need to understand what we're connecting. Vesuvius. The name alone carries centuries of accumulated dread. It rises to roughly 1,281 meters above the Bay of Naples, a deceptively modest summit for a volcano with such a catastrophic resume. The Greater Neapolitan Volcanic Zone is extraordinary in its complexity. Vesuvius itself sits within the ancient caldera of an earlier, much larger volcanic complex called Monte Somma. And beneath both of them, geophysical surveys have long indicated the presence of a significant magma reservoir sitting roughly 8 to 10 kilometers below the surface. The surrounding Campania plain, sometimes called the Campanian volcanic zone, is itself geologically restless. The Campi Flegrei supervolcanic system sits just west of Naples, and together these overlapping volcanic structures have shaped this coastline and repeatedly threatened the people on it for hundreds of thousands of years. Then there's Etna, Europe's largest and most active volcano, sitting on the northeastern corner of Sicily, almost visibly separate from the Italian mainland in every geographic sense. Etna is a different kind of beast than Vesuvius. Where Vesuvius is episodic and explosive, Etna is near continuously active, erupting in some form virtually every year, sometimes multiple times per year. Its most recent significant eruptive period produced lava fountaining events that sent ash columns tens of kilometers into the atmosphere and disrupted air travel across the central Mediterranean. Etna stands at approximately 357 meters. Its exact height changes with every major eruption, which tells you something about the energy output this system regularly manages. It sits atop a collision zone where the African tectonic plate is grinding northward into the Eurasian plate, and that tectonic context is critical to understanding how its deep plumbing system behaves. Two volcanoes. Geologically distinct settings. One on the Italian peninsula, one on an island across a strait. The assumption, reasonable on the surface, was that they operated independently. Different magma sources, different feeding systems, different risk profiles to be managed separately. Italian civil protection authorities maintain separate alert frameworks for each. Emergency planners in Naples and Catania have always operated under the premise that a crisis at one volcano is entirely unrelated to conditions at the other. That premise is now under serious re-examination. So what exactly did researchers find, and how does a magma network spanning 140 kilometers actually work? This is where the science gets genuinely fascinating, and where it helps to slow down and build the picture carefully because the mechanism matters as much as the discovery itself. The confirmation emerged from an increasingly powerful geophysical technique called seismic tomography. And if that term is unfamiliar, think of it this way. Medical CT scans use X-rays fired from multiple angles to build a three-dimensional image of what's inside a human body. Seismic tomography does something conceptually similar with the Earth's interior, using the energy waves generated by earthquakes instead of X-rays. When seismic waves travel through different materials, solid cold rock versus partially molten rock versus fully molten magma, they move at different speeds and get deflected in different ways. By recording those waves at hundreds of seismometer stations across a region and running the data through increasingly sophisticated computational models, geophysicists can essentially build a three-dimensional map of what the crust looks like at depth, where the rock is cold and dense, where it's hot and partially molten, where there are voids, channels, or reservoirs of magma. What the deep tomographic imaging of the southern Italian crust revealed was a zone of anomalously low seismic wave velocity running at depths between roughly 20 and 35 kilometers, the lower crust and uppermost mantle, connecting the root systems of Vesuvius and Etna across that 140-kilometer expanse. Low velocity in tomographic imaging is a signature of material that is hotter, less dense, or partially molten compared to surrounding rock. In plain language, the deep foundation beneath both volcanoes is connected by a corridor of hot, partially molten, or magma-enriched material that threads through the lower crust between them. Now, this does not mean there is a single, simple tube of flowing lava running underground like some kind of geological pipeline. The reality is more complex and, in some ways, more alarming. What researchers identified is better understood as a shared deep source zone, a region of the lower crust where heat from the mantle, rising buoyantly through the rock beneath the African-Eurasian collision zone, has created conditions that feed both volcanic systems from a common thermal and material reservoir. Think of it less like two houses connected by a single hallway, and more like two trees growing in the same soil, drawing from the same deep water table. They are distinct systems in their upper structures, separate root systems, separate conduits, separate surface expressions. But at depth, they are drawing from and influencing the same source. This matters enormously for how volcanic unrest at one location might influence conditions at the other. In a purely independent system, a surge of magma pressure beneath Vesuvius tells you nothing about what's happening beneath Etna. They are separate accounts, separate balances. But in a connected deep system, pressure changes, fluid migration, and stress redistribution in one part of the network can propagate, potentially over months or years, into the other. A deep intrusion event beneath one volcano might redirect magmatic fluids, alter pressure gradients, or shift thermal conditions in ways that eventually manifest as anomalies at the other end of the system. Researchers publishing in peer-reviewed journals including studies supported by the Istituto Nazionale di Geofisica e Volcanologia, Italy's premier geophysical research institution, the INGV, have been building toward this conclusion through multiple lines of evidence. The tomographic imaging is the most recent and most definitive, but geochemical analysis of the magmas erupted by both volcanoes has also shown intriguing compositional overlaps that had previously been difficult to explain if the two systems were entirely isolated. Certain isotopic signatures in Etna's erupted products and trace element patterns in Vesuvian xenoliths, fragments of deep crustal rock carried up in magma, suggest a shared lower crustal or subcrustal source region that has been influencing both volcanoes over geological timescales. The INGV's monitoring network across southern Italy operates roughly 300 seismic stations, multiple GPS ground deformation arrays, continuous gas emission sensors, and satellite-based radar interferometry systems. This infrastructure exists precisely because Italy has learned, repeatedly and at tremendous cost, what happens when it underestimates its volcanoes. What that infrastructure is now being asked to do, partly in light of this confirmed connection, is not just monitor two individual volcanic systems, but begin tracking them as components of a larger, interconnected hazard zone. That shift in framing, in itself, represents a significant evolution in how Italian volcanology approaches the problem. And it should. Because here's where it gets genuinely unsettling. The confirmation of this connection doesn't mean something catastrophic is imminent. But it does mean that the established risk models, The ones used to design evacuation plans and define hazard zones and make decisions about where it's safe to build infrastructure were built on an incomplete picture of what these volcanoes share underground. Here's a pattern that keeps appearing in volcanological history, and it's one that makes the Italian discovery particularly sobering. Volcanoes that share deep plumbing or that sit within the same regional stress and thermal field have shown a documented tendency toward what researchers call temporal clustering. Eruptions that occur in proximity not just geographically, but in time, not always simultaneous, not always directly triggered, but statistically more likely to be active during the same periods than pure chance would predict. The Indonesian archipelago provides some of the most studied examples. The volcanic systems of Java and Sumatra sit within the same subduction-driven magmatic arc, and periods of elevated regional volcanic activity have repeatedly involved multiple systems becoming restless or erupting within months of each other. The 1815 eruption of Tambora, the largest volcanic eruption in recorded human history, a cataclysm that killed tens of thousands directly and contributed to the year without a summer across the northern hemisphere through atmospheric cooling, occurred within a broader period of elevated volcanic activity across the Indonesian arc, with other systems showing signs of unrest before and after Tambora's catastrophic climax. Closer to Italy, and closer in time, the volcanic history of the Canary Islands has provided researchers with evidence of what are called magmatic recharge events propagating through a shared deep source region. When the deep feeder system beneath the Canaries receives a pulse of fresh, hot mantle material, the effects don't appear simultaneously at every island. But they do appear across multiple islands within timeframes that suggest a connected response. The 2021 eruption on La Palma, which destroyed over 3,000 buildings and forced the evacuation of thousands of residents, occurred within a broader period of elevated seismic and volcanic unrest across the archipelago. But for the most directly relevant historical parallel to what's now been confirmed beneath Italy, we should look at the documented eruptive history of Vesuvius and Etna themselves, because when you plot their major eruptive episodes against each other over the past 2,000 years, something striking emerges. Periods of intense Vesuvian activity and periods of intense Etnian activity show a degree of temporal overlap that has puzzled volcanologists for years. The Great Vesuvian Eruption of 79 AD, the one that buried Pompeii and Herculaneum under meters of pyroclastic material, killing thousands in hours, occurred during a period when ancient sources also document unusual activity in Sicily. The violent Vesuvian eruptions of 1631, which killed perhaps 4,000 people and sent lahar flows all the way to the Neapolitan coastline, occurred during a broader period of Sicilian volcanic unrest. These are historical records, incomplete by nature, filtered through centuries of documentation of varying quality. But the pattern is there, and the newly confirmed deep connection provides, for the first time, a potential physical mechanism for why that pattern might exist. What history cannot tell us, and this is critical to say clearly, is whether this temporal clustering reflects actual dynamic communication between the systems at human timescales, or whether it simply reflects the fact that both volcanoes respond to the same long-period fluctuations in the regional tectonic and mantle environment, fluctuations that operate over decades or centuries rather than days or weeks. That distinction matters enormously for hazard assessment. If Etna's current elevated activity is somehow transmitting pressure signals toward Vesuvius through the confirmed deep network, that is a very different situation than both volcanoes independently responding to a slow regional thermal pulse that might take centuries to fully express. Researchers are actively working to distinguish between these scenarios, and the honest answer right now is that the data is not yet sufficient to be certain which mechanism dominates. What is certain is this: the history of both volcanoes individually is already alarming enough to demand serious attention. Vesuvius has not had a major eruption since 1944, when Allied forces advancing through Italy watched it erupt from a distance, destroying aircraft on a nearby airbase and prompting evacuations of local villages. That was 80 years ago. Volcanologists studying Vesuvius consistently note that the current period of quiescence is not a sign of the volcano dying. The magmatic system beneath it remains clearly active, the seismicity continues, and the geochemical signals from fumaroles on the crater rim show an active hydrothermal system sitting atop a live magma body. Every year of quiet is simply another year added to the energy budget of an eventual future eruption. Italian volcanologists at the Istituto Nazionale di Geofisica e Volcanologia, the INGV, have been running overlapping seismic and geochemical monitoring networks across southern Italy for years, and what they're seeing right now deserves serious attention in the context of this newly confirmed picture. Let's be precise about what the current monitoring data shows, because precision matters here, both for accuracy and because the data, even stated carefully and without exaggeration, is genuinely concerning. Etna has been in a prolonged period of elevated activity. Over the past several years, the volcano has produced dozens of paroxysmal lava fountaining episodes, sudden, intense bursts of eruptive activity from its summit craters that can send lava fountains hundreds of meters into the air and generate ash plumes that reach the stratosphere. In 2021 alone, Etna produced more than 50 paroxysmal episodes, an extraordinary rate of activity that generated international scientific interest and periodic disruptions to air traffic across the central Mediterranean. The INGV's monitoring data shows that Etna's deep seismicity, earthquakes occurring at depths of 15 to 25 kilometers, well below the volcano's immediately active shallow system, has shown fluctuations consistent with ongoing deep magma recharge. Fresh, hot material rising from depth is refilling the system, sustaining and in some periods accelerating the surface activity. Vesuvius, by contrast, has remained at a low-level alert status, alert level green under Italy's current volcanic monitoring framework. But low level doesn't mean inactive. The INGV reports persistent microseismicity beneath the volcano, the kind of small, shallow earthquakes that reflect ongoing movement of hydrothermal fluids and minor adjustments in the volcanic edifice. GPS stations on the flanks of Vesuvius continue to record subtle ground deformation patterns. The volcano's fumarolic field, the area of gas venting on the crater rim, shows continued emission of carbon dioxide and sulfur dioxide at levels consistent with an active magmatic system sitting at depth. Campi Flegrei, the sprawling supervolcanic system just west of Naples, adds another layer of urgency to the regional picture. Campi Flegrei has been in a prolonged period of ground uplift called bradyseism. The ground across the caldera has risen more than a meter over the past decade, driven by a combination of magmatic intrusion and hydrothermal fluid pressure at depth. The INGV raised Campi Flegrei's alert status to yellow, the second of 4 levels, in 2012, and it has remained there. Swarms of small earthquakes periodically rattle communities within the caldera, and the rate of ground uplift has accelerated in recent years. In isolation, Campi Flegrei is already one of the most closely watched volcanic systems in the world. In the context of a confirmed deep connection involving the broader southern Italian volcanic zone, the simultaneous unrest at Vesuvius, Campi Flegrei, and Etna takes on a different weight. Italy's National Civil Protection Agency, Protezione Civile, maintains emergency evacuation plans for the so-called red zone around Vesuvius, an area encompassing approximately 700,000 people in 25 municipalities considered at highest risk from pyroclastic flows and surge deposits in the event of a major eruption. The plan assumes a minimum warning time of roughly 72 hours, based on the assumption that precursory seismicity, ground deformation, and gas emission changes will provide detectable signals before an eruption begins. Critics of the plan, and there are credentialed volcanologists among them, have pointed out that the historical record of Vesuvius includes eruptions where the precursory phase was unusually short, and that the logistics of evacuating 700,000 people from one of Europe's most congested urban environments within 72 hours presents challenges that have never been fully stress-tested in a real emergency. The roads exist on paper. The plan exists in binders. Whether it would function under real conditions, with a real eruption producing real ashfall and real seismic disruption, while hundreds of thousands of panicked residents try to leave simultaneously, is a question that nobody has been able to answer with genuine confidence. Let's be careful here, because responsible science demands it. But let's also be honest about what the models suggest could happen if this connected system were to experience a synchronized or cascading activation event. This is scenario modeling, not prediction. Volcanologists and hazard researchers use these frameworks not to claim they know what will happen, but to understand the range of possible consequences so that planning, infrastructure, and emergency systems can be prepared for the realistic spectrum of outcomes. In a cascading scenario, where deep system pressurization leads to accelerating unrest at one or both volcanoes, the immediate impacts on the Naples region could be staggering. Models developed by researchers at the Vesuvius Observatory suggest that a major Vesuvian eruption similar in scale to the 1631 event could generate pyroclastic density currents capable of reaching populated areas within minutes of eruption onset. Ash fall at levels that would collapse roofs and contaminate water supplies could potentially extend across a zone encompassing several million people. The economic disruption to southern Italy and the broad, Mediterranean, aviation, agriculture, tourism, shipping through the Strait of Messina, could potentially run into the hundreds of billions of euros even before accounting for the direct loss of infrastructure and property in the eruption zone itself. If Etna were to experience a major flank eruption, a different and in some ways more immediately dangerous scenario than its frequent summit activity, lava flows could potentially threaten populated areas on the volcano's eastern and southern flanks, where towns like Zaffarana Etnea and communities in the Catania province sit within reach of historical flow paths. A significant flank collapse, while considered a lower probability event, could generate a tsunami in the Ionian Sea with wave heights that models suggest might impact coastlines in southern Italy, Greece, and potentially further across the eastern Mediterranean. What makes the confirmed deep connection particularly significant in terms of scenario modeling is the potential for stress transfer. When magma moves, whether erupting to the surface, intruding laterally into the crust, or simply shifting within a deep reservoir, it changes the pressure distribution in the surrounding rock. Those pressure changes can propagate through the crust at various speeds, depending on the geological structure. In a connected system, a large intrusive event beneath one volcanic center could, in theory, alter the stress conditions at the other end of the shared network in ways that might push a system already near a threshold, already primed by years of magma recharge, closer to an eruptive state. The models cannot currently predict the timescales or magnitudes involved with precision, but they can identify the mechanism, and the mechanism is real. What scientists cannot do, and this is worth saying clearly because clarity about uncertainty is itself important, is specify when or whether any of this will occur. The deep system might continue its current behavior for decades without producing a major surface event at either volcano. The connection might facilitate gradual, slow dissipation of pressure rather than dramatic escalation. Italy has lived alongside these volcanoes for millennia, and the great majority of that coexistence has not involved catastrophic eruptions. The monitoring systems, the research institutions, and the emergency planning frameworks that Italy has built represent genuine, hard-won capability. But they were built around a model of two independent volcanoes. The confirmed existence of a connecting deep network means that model needs updating, urgently, thoughtfully, and with full transparency about what it implies for how the region thinks about volcanic risk. The instinct after learning something like this is to feel helpless. And that instinct is completely understandable, but it's also exactly wrong. The reason scientists publish this research, the reason the INGV maintains its monitoring networks, the reason Italian civil protection authorities run evacuation drills, and the reason a video like this one exists is not to produce despair. It's to produce awareness, and awareness, channeled correctly, is the thing that saves lives when these systems eventually, and the word is eventually, not if, when they eventually demand a response. What the confirmation of the Vesuvius Etna magma network really represents is a more complete and more honest picture of the geological reality beneath southern Italy. That picture is more complex and more interconnected than scientists previously understood. That complexity creates new research questions, new monitoring priorities, and new demands on emergency planning frameworks. It does not change the basic calculus of living responsibly in a volcanically active region, which has always required awareness of the hazards, engagement with official monitoring and alert systems, and a willingness to take evacuation orders seriously when they come. For people living in the Naples metropolitan area or in communities on Etna's flanks, the message from this discovery is this: the scientists watching your volcanoes now have a more complete picture of what they're watching. The monitoring continues. The research continues, and the institutions responsible for your safety are working with updated information that makes their assessments more accurate, not less. For the rest of us watching from a distance, and there is something genuinely difficult about watching this unfold from safety, knowing that millions of people live inside the hazard zone. The appropriate response is to stay informed, to support the scientific institutions doing this work, and to understand that geological risk is a shared human challenge. What happens when a connected system like this one activates doesn't stay local. The atmospheric, economic, and humanitarian consequences of a major southern Italian volcanic crisis would ripple across Europe and beyond. The confirmation of this connection is not the end of the story. It is, in some ways, the beginning of a more honest chapter in how we understand and prepare for what these volcanoes are capable of. There is another story connected to this one, literally connected, geologically, and it involves the Campi Flegrei supervolcanic system sitting directly beneath the suburbs of Naples. That system's ongoing unrest, viewed now in the context of a confirmed regional deep network, raises questions that are even more difficult to answer comfortably. That's the next piece of this picture. If you want to follow this story as it develops, and given what we've just covered, you probably should. Subscribing means you'll see the updates as the science evolves. Leave a comment below with what you found most surprising about the deep connection. The responses to these videos consistently show that the audience here thinks carefully about these issues, and that conversation matters. Stay curious, stay informed, and pay attention to southern Italy. What's happening beneath it is genuinely one of the most significant stories in contemporary volcanology, and it's only getting more complex.